So now we're going to take a look at how we conduct the paired t-test. So this is separate from the two-sample t-test, as the title suggests, we have paired data. So you always have to be careful when you get a question to check if you have two samples of data or if you have paired data. If you have paired data, then the usual ones that this test gets mixed up with is the sign test and the Wilcoxon rank sign test, as both of those also used paired data. So remember that paired data is where you are looking at the same information about the same person or place, but at two different times, usually before and after something has happened. Always be careful. If it states that the data is symmetrically distributed, then it's not necessarily meaning that it's normally distributed and therefore is suggesting the Wilcoxon rank sign test. If it states that the data is definitely not symmetrically distributed, then you should be using the paired sign test. If it states that the data is normally distributed, then you should be using the paired t-test. So always be careful when you get a question with paired data that you are being careful as to which one you are doing and which one you're being expected to use. So when we have paired data, we can use the t-test to look at statistically significant difference in the data. Now, if you don't have a graphical calculator, you are going to have to use this formula here to find your test statistic. And unfortunately, it isn't explicitly written in the formula booklet either. However, because we have our graphical calculator, we are going to be using that instead to find our test statistic. So, either way, you still need to find the differences between the two variables and the standard deviation of those differences and the mean of the differences. So you're finding the differences and then you're finding the standard deviation and the mean of those differences. Again, as the difference of the two means and the single t-test, we're going to be using the critical value table for the t, which remember is on page 19 of your formula booklet. And this time our critical value, our degrees of freedom that we use to find our critical value is going to be the number of pairs of data minus 1. So do be careful with that. We do have paired data, but because we're only looking at the differences, we're then treating it as one set of data. So the degrees of freedom is going to be the number of pairs that we had minus 1. And as before, if we are using two symbols, then we need to make sure that we are explaining what each of the symbols means. You could use the mean difference as your symbol instead and talk about the mean difference being greater than 0 or less than 0 in the same way as we did with the two sample sign test and the two sample Wilcoxon rank sign test. But sometimes pupils find it hard, especially with one-tailed test, to decide whether it's going to be greater than 0 or less than 0. So we try and get around that here by using the symbols. So, for our first example, we have 16 children participated in a study to examine the effect of athletic activity on heart rate. 8 of the children were competitive swimmers and the other 8 were normal, lazy and healthy children. A lazy child was chosen to match each swimmer with respect to age, height, weight and body surface area. And we're going to talk a little bit later on about why this was important to do when we get onto the experimental design section. But that means that we have paired data because each of these swimmers has been paired with someone who was similar to them. So here we have the table that shows the children's heart rates in beats per minute. And we can see there we've got pair 1, pair 2, pair 3 and so on. So to start off with, we have what does paired in respect to age, height, weight and body surface area mean? Well, this is actually telling us that they have tried to limit what is called experimental error. By limiting the difference between the participants and you can also say that then any difference that is found is likely to be due to their activity level, not a different variable. So we're trying to make it so that anything that we find is due to what we are looking at, not a different variable that we're not testing. So for part B, why pair the children like this instead of comparing the averages of the two samples? Well, if we have all the lazy people being maybe all taller or shorter, and if we have the swimmers being more athletic, already being smaller, then that could mean that it was the heights or the weights or whatever that was making the difference, not their activity level. So again, this is similar to the second sentence that I put here. So that any difference found is due to their activity level, not their age, height, weight. Body surface area. So we're trying to limit the amount of things that are going to affect it. So we're trying to now carry out the chosen test at 5% significance level. So in the question, it's just saying effect of athletic activity on heart rate. It's not saying that they think the athletic pupils are going to do better or worse than the lazy children. So that means that we have a two-tailed test. So our H0 would be that mu L equals mu A. And our H1 would be that mu L is not equal to mu A. And this is where mu L is the population mean heart rate of a lazy child, and mu A is going to be the population mean heart rate of an active child. So then we need to find the differences. Now you could just do your subtractions, or you can use your graphical calculator to help you to do this. So in your graphical calculator, I'm going to type the lazy children's heart rates into list 1. And I'm going to type the swimmers into list 2. As always, quickly double check that you have entered them all incorrectly. I mean, these numbers are quite nice, so you could have just kept the, you could have just done the subtraction yourself, but then once you've entered your data, if you go up so that where it says list 3, it's highlighted as it is in my calculator now. If we tell the calculator to do shift list 1 minus shift list 2, it needs to be that bit there that's highlighted. So it's shift and then 1 to get list 1 minus shift and then list again 2. When I click EXE now, list 3 has been filled out with the differences. Now it's quite important that we tell the examiner which way we have done our takeaway. So we have done lazy minus swimmer. You have to especially do this if instead of writing your hypothesis like this, you've decided to write it with the mean difference. It's exceedingly important that you say which way you've done your takeaway then, because they need to know which way you have done that, because that's going to affect the values that you get. So we then need to write down our differences. So we're going to have pair 1, 2, 3, 4, 5, 6, 7, 8. And our differences are -5, 10, 0, 35, 15, 25, 15, 20. This is to show our method. Because we already have the values in our calculator, we can direct our calculator to now find the information that we need. Remember that we need to find the mean and the standard deviation of the differences. If you've done it by hand, you are going to have to type them in anyway. But still write them down first because it's showing your method of process. So what we need to do is we need to go into calc. And because we're trying to find the information related to the differences, which are in list 3, we need to go into our set option and we need to tell it to look at list 3. So we've put our one variable, which is the difference, and that is in list 3. So you have to click F1 to get the list option up, then click 3 and then exit, and it should then say list 3. We don't have any frequencies, so we want that second option there to just say 1 as it does there. And then when I go into 1 var, this is the information that I need to write down. So the information that we've got is that the mean of the differences is 14.375. The sample standard deviation of the differences is 12.9387292. And again, notice I've wrote the whole thing down here because I'm doing a further calculation with it. Don't start rounding at this point. And the number of pieces of data that I have is 8. So now we're going to go back and we're going to be going into test T, and we're actually going to go into one sample because we're treating it as one sample of the differences. So we go into one sample. We need to make sure that this part here is the same as our hypothesis, so in this case not equal to. Because we don't have any values that we're adding on to either side, we're just going to have that as 0. The mean here is 14.375. The sample standard deviation is 12.9387292. And the number of pieces of data that we have is 8. And there we have our T, which is 3.14. That is our test statistic. Before we find our critical value, we need to write down our degrees of freedom. So that's the number of pairs of differences. So that's the number of differences that we have, which is 8 minus 1, which gives us 7. Because this is a two-tailed test, just as we did with the 1 sample T and the 2 sample T, we have to half our significance level, so that goes down to 2.5%. 100% take off 2.5% means that we're looking down from 0.975 across from 7 degrees of freedom, which gives us a critical value of 2.365. So in the same way as we did with the 1 sample and the 2 sample, as the test statistic is bigger than the critical value, that means that we reject H0 at a 5% significance level. There is sufficient evidence to suggest the heart rate for, sorry, that should say the mean heart rate. So the mean heart rate for lazy children is not the same as the swimmers. And again, we need to be careful here because we need to make sure that it's hitting those 2 assumption points. So again, does it say here in the question that the heart rates were normally distributed? No, it doesn't. Does it say here that the 8 children are a random sample? No, it doesn't. So we need to write those down as assumptions. Now this time we write them slightly differently. So our assumption first of all, that the swimmers are a random sample, which is fine, that's the same as what we usually have. But then we have 2 options for the way that we write our second assumption. So option 1 is that the differences are normally distributed. And by differences, we're meaning the differences between the lazy and swimmer heart rates. Or we can say that both lazy and swimmer heart rates are normally distributed with a common variance. So these 2 are telling us the same thing, but we need to be careful and make sure that we are writing them down. Now this is summarised on the next page, so you can see here the assumptions. So both sets of data need to be normally distributed with common variance, which we could also say that the difference between the 2 sets of data is normally distributed. So I'd like you to pause the video now and give the Now You Try question a go. So hopefully you paused the video there. So this time we're trying to see, are the sense measurements on average lower after hypnotism? So we've got a study was conducted to investigate the effectiveness of hypnotism in reducing pain. Results of randomly selected subjects are shown in the table. The before value is matched with the after value. So this is one person before hypnosis and after hypnosis. This is a separate person and so on. Are the sense measurements on average lower after hypnotism? Test at a 5% significance level. So we want H0, mean before equals mean after. H1, mean before is more than mean after, because we're wanting after to be smaller. Where mu B is the population mean pain sensor measurement before hypnosis, and mu A is the population mean pain sensor measurement after hypnosis. So again, I did before minus after. As you can see in my calculator, I put the befores into list 1. I put the afters into list 2. The data here is going across, but make sure you put it down in your calculator. And then remember to go up to where it says list 3 at the top, and then you click in shift list 1 minus shift list 2, and it'll fill out that third list for you. I've wrote this down here. Just be careful with adding stuff to the actual where the question is. Usually that will be seen and marked along with the rest of your answers, but just make sure it's really clear that you've written it on so that it doesn't get missed in the marking. So then finding the information about those, making sure again that your set says list 3 because we want it to be looking at those differences. And then our mean is 3.125. Our sample standard deviation is 2.91143067. And the number of pieces of data that we have is 8. Going into test T, 1 sample. This time it's a one-tailed test. So as you can see, I've got greater than 0 there. The mean is 3.125. The sample standard deviation and the number of pieces of data are written in there, which gave us 3.04 to 3 significant figures. Looking at our degrees of freedom, 8 minus 1 gives us 7. And this time, because it's a one-tailed test, we're going to be looking down from 0.95 across from 7, which gives us 1.895. So as the test statistic is bigger than the critical value, we reject H0 at a 5% significance level. There is sufficient evidence to suggest that the mean pain sensor measurement is higher before hypnosis than after. And again, in our description here, nothing about normally distributed. It does say about a random sample, randomly selected. So our assumption is that the difference between the pain sensor measurements before and after hypnosis are normally distributed. Just to point out again in the calculator, don't forget you also have the p-value here. This p-value means that we have 0.009478 would be our chance of this happening. We're comparing that to 0.05 for 5%, so we would be expecting to reject H0. But that's something that we can quickly double check. Is the probability of this happening less than my significance level? Yes, it is. So that means that I should be expecting to reject H0. Thank you very much for listening.